Hello students, we are discussing about the different periodic properties in periodic table, and we have discussed about size, electronegativity, electron affinity, oxidation and reduction, and metallic character or non-metallic character. These are few important periodic properties which depends on various factors. So first one is size or atomic radius. So atomic radius, actually if we consider it's an atom, then the distance between the nucleus and the valence shell is known as atomic radius, and this atomic radius actually totally depend on the attraction force between this valence electron and the nucleus. If the attraction between valence electron and nucleus increase, then radius of the atom or atomic radius decrease, as well as if the attraction between nucleus and valence electron increase, then the size of the atom or atomic radius actually increase. So we can say the attraction between nucleus and valence electron is inversely proportional with the size. If attraction increase, then size decrease, as well as if attraction decrease, then size increase. Now this atomic radius, how this atomic radius actually change when you move to according to periods or according to group. So if the principal quantum number of the valence electron, that is n, if principal quantum number of the valence electron increase, then the atomic radius increase. So principal quantum number of the valence electron directly proportional with the radius. For example, if you know lithium and sodium, lithium have 3 electron and sodium have 11 electron. So the electronic configuration of lithium is 1s2 2s1. So that is valence electron, that is 2s1. Similarly, the electronic configuration of sodium, that is 1s2 2s2 2p6 and 3s1. So this 3s1 actually the valence orbital or valence electron. So if you notice that the principal quantum number of the lithium is 2, this 2 is principal quantum number, whereas for sodium the principal quantum number is 3. That means in case of lithium the principal quantum number is 2, and in case of sodium the principal quantum number is 3 for valence electron. Therefore the size of sodium and lithium follow this order, that lithium have smaller size than sodium. Why? Because the principal quantum number actually increase for sodium. So in case of lithium, the valence electron actually present in the second shell. Why? Because the principal quantum number of the lithium is 2. That means the valence electron present in the second shell. Whereas for sodium, the valence electron actually present to the third shell. That means in case of sodium, the distance between the valence shell and the nucleus actually increase. Therefore, sodium have a larger size than lithium. Similarly, if we move from left to right in the periodic table, then actually the size of the element decreases. So if we move from left to right in the periodic table, for example carbon, nitrogen, oxygen and fluorine, the number of electron for carbon is 6, for nitrogen is 7, for oxygen is 8, and for fluorine it is 9. Similarly, the number of proton also equivalent with the number of electron, that is 6, 7, 8, 9. Therefore, in case of fluorine, there present 9 electron and 9 proton. So therefore, attraction between this nucleus and valence electron actually increase, or they are present more attraction force compared to this carbon, because in case of carbon they are present 6 proton and 6 electron. Therefore in case of fluorine they are present more attraction force, and in case of carbon they are present less attraction force. Therefore the size fluorine have a smaller size than oxygen, then nitrogen, then carbon. So this is actually size order. So we can say if we move from left to right in the periodic table, then size of the element actually decrease, and if we move from top to bottom in the periodic table, then size of the element actually increase. Clear? Sometimes the size of the element depend on the oxidation number. If oxidation number increase, then size of the element decrease. So we can say oxidation number is inversely proportional with the size. For example, if you want to compare the size between Fe plus 2 and Fe plus 3, then you know Fe plus 3 have higher oxidation state, and therefore the size of the iron is less than Fe. Similarly, you know manganese plus 2, manganese plus 5. If you consider that manganese plus 5 would have higher oxidation state than manganese plus 2, therefore manganese plus 5 have smaller size than manganese plus 2. This is the relation between oxidation state and the atomic radius. Next one is electronegativity. I think you know about this electronegativity. Electronegativity means tendency for attraction electron, or tendency to attract electron or bonded electron towards itself. It is known as electronegativity. For example, A and B bonded together and there present 2 electrons in between them. So sometime this element attract this 2 electron towards itself. Therefore electron density shift towards the A element, just like this. There present more electron compared to B. This property of the elements actually known as the electronegativity. And you know this electronegativity directly proportional, and you know this electronegativity inversely related with the size. So if size of the element increase, then electronegativity of the element actually decrease. Therefore we can say size is inversely proportional with the electronegativity. For example, again if we take fluorine, chlorine, bromine and iodine, therefore you know the size order of this halogen element is iodine greater than bromine greater than chlorine greater than fluorine. That means iodine have larger size than bromine, and bromine also have a larger size than chlorine, and fluorine is the smallest element among this group. So this is the size order. But the electronegativity order of this element totally opposite. That is, fluorine have more electronegativity than chlorine, than bromine, than iodine. So you can say size is inversely related with the electronegativity. Next one is electron affinity or electron gain enthalpy. So electron affinity also related with the atomic radius, and this electron affinity sometimes directly proportional with the electronegativity and also inversely related with the size of element. Therefore if electronegativity increase, that means electron affinity increase, but if size decrease, then electron affinity also increase. So electron affinity inversely related with the size. But there are some exceptions, that is, you know, fluorine and chlorine. Fluorine have a smaller size than chlorine, therefore it is expect that fluorine have higher electron affinity than chlorine, but this is not actually not happen. Here chlorine have more electron affinity than fluorine. Why? Due to the orbital size. You know, chlorine have 3p orbital to their valence shell, whereas fluorine have 2p orbital to the valence shell. And the size of 3p orbital is larger than 2p orbital. Therefore, after addition of electron to their valence shell, there present a electronic repulsion in case of fluorine due to the smaller size of 2p orbital. But in case of chlorine, if chlorine gain electron to their valence shell, then due to this larger size, the electronic repulsion or electron-electron repulsion slightly smaller than fluorine. Therefore, chlorine have higher electron affinity than fluorine. And it is also true that third periodic element have higher electron affinity than second period element. For example, sulfur also have higher electron affinity than oxygen. Similarly, chlorine also have higher electron affinity than fluorine, and also phosphorus whose electron affinity more than nitrogen also. So in general, you can remember this, that third period element have always more electron affinity than second period element. Next one is ionization energy. And you know, this ionization energy means the amount of energy required to remove electron from the valence shell. And this ionization energy also dependent on the attraction force between the valence shell and nucleus. So if size of the element decrease, therefore there present more attraction force, so ionization energy of the element actually increase. So this is the simple relation between the ionization energy and size. And if X an element, and if you want to remove an electron from this X element at the ground state, then this X element transfer into unipositive element or unipositive ion. So you have to provide some amount of energy. So this energy actually called first ionization energy. So first ionization energy means removal of one electron from the ground state. Second, if you want to remove second electron from this unipositive cation, then again you have to provide some amount of energy. So this is known as ionization energy 2. And after removal of electron from this X plus, it transfer into X2 plus or divalent element. Similarly, if you want to remove third electron from this divalent cation, then you have to provide again some amount of energy. This energy actually known as ionization energy 3, that means third ionization energy, and it transfer into X3 plus. So first one is ionization energy 1 or first ionization energy, second ionization energy, and then third ionization energy. So if principal quantum number of the valence electron increase, then you know size of the element actually increase, therefore ionization energy decrease. So this is a simple relation between the principal quantum number of and the ionization energy. So if principal quantum number of the valence electron increase, then ionization energy decrease. Next one is metallic character. And you know, metallic character dependent on the free electron which is present to the valence shell. Free electrons means that electron which are loosely bound by the nucleus. That means if the size of the element increase, then the distance between the nucleus and the valence electron actually so actually if size increase, then the attraction between the nucleus and the valence electron actually decrease. Therefore the metallic character increase. So we can say size is directly proportional with the metallic character. Therefore if size increase, then metallic character also increase. So if you move from top to bottom, then for example carbon, silicon, germanium, tin, lead, then if you move from top to bottom to the periodic table, then size of the element actually increase. Therefore, the metallic character also increase. So size directly proportional with the metallic character. Similarly, if you move from left to right to the periodic table, then the size of the element actually decrease. Size of the element actually decrease. Therefore, metallic character also decrease. Elements are normally metal, whereas if you move from group 14, 15 or 16 or 17, then these elements are non-metal in nature. Therefore, if you move from left to right, then metallic character actually decrease. So these are periodic functions, and these periodic functions or periodic properties totally depends on size and electronegativity also, and they are related with each other. Thank you.